In the eye of the transformer, global-local correlation for egocentric gaze estimation. Understanding eye movements and gaze activity is essential for understanding human intention during daily activities. While wearable eye trackers are a standard way to measure a person's gaze behavior, they require calibration, consume substantial power, and add complexity to wearable systems. In this work, we address the task of egocentric gaze estimation, which alternatively seeks to localize the visual attention of a camera wearer from first-person video. In this task, the input is a video sequence, and the output is the gaze prediction in each frame. We represent the output as a gaze heat map, and therefore formulate the problem as a pixel-wise prediction task. There are multiple prior works that address egocentric gaze estimation. These works span predicting gaze in a single frame, anticipating potential gaze locations in the future, and jointly modeling gaze and action recognition. These works provide a solid foundation in egocentric gaze estimation and show the importance of gaze in egocentric vision understanding. However, all of these works use convolutional neural networks as their backbone architecture. Transformer architectures have therefore not been applied to address this problem yet. In our work, we leverage the latest advance of the vision transformer and build the first transformer-based model for egocentric gaze estimation. Global visual context is critical in accurate gaze prediction. In the picture in the middle, the green dot represents a gaze target captured by an eye tracker. There are lots of objects in this frame that might be potential gaze targets, but we can infer which region contains the gaze target because another person is pointing at and looking at the piece of paper they are holding. We can infer that the wearer is likely to look at this piece of paper as well. This is easy for a human because we understand the scenario with a global perspective. Even though transformers model the correlations across local visual features to get a large receptive field, as we show on the left, global local correlation is not captured in the self-attention mechanism. This is insufficient for a powerful and robust gaze prediction model. In this paper, we first build a transformer-based model. Then, we embed global context explicitly and model the connection of local and global features with our novel global local correlation module. This slide presents an overview of our model. The whole model is composed of 4 modules: visual token embedding, the transformer encoder, global local correlation, and the transformer decoder. The visual token embedding module takes a sequence of video frames as input. Then, it divides input into local patches and encodes them into local visual tokens using a convolutional layer. This is a standard operation in the transformer architecture. In our work, we take a step further and embed global visual context into a global token using additional convolutional layers. Note that we only add a learnable position embedding to local tokens. Then, the embedded tokens are input into a transformer encoder. We utilize the multi-scale video transformer model, which is a state-of-the-art in vision understanding, as our backbone. Global features are integrated into local tokens by calculating their correlations in standard self-attention layers. However, both global and local tokens are treated equally in the encoder, so global local correlations would be diluted by many more correlations across local tokens. This could be a limit to fully utilizing global scene information. To address this bottleneck, we propose a novel global local correlation module attached to the encoder. Regular self-attention in our encoder models the correlation of each token pair, while the global local correlation module ignores all correlations across local tokens and only calculates all global local correlations. In this way, we break the equivalence of all token relationships and emphasize the connection of global and local features. Output from the global local correlation module is concatenated with the output from the encoder along the channel dimension. Finally, we replace the pooling operation in the encoder block with trilinear upsampling to build a transformer-based decoder. The decoder upsamples features to a higher resolution. To elaborate on our global local correlation module, we can compare the mathematical equation for regular self-attention with our proposed global local correlation. Suppose the global token is in the first row among all tokens. In regular self-attention, we calculate correlation directly using query and key matrices and then reweight the value using normalized weights. In global local correlation, we use a suppression matrix that has zeros on the first column and diagonal and assigns a very large value, lambda, on the other entries. By abstracting this matrix, the correlations across local tokens are suppressed to be very small values, which are nearly zero after softmax. In this way, we emphasize global-local correlations and de-emphasize all local correlations. Our proposed model is validated on two datasets with egocentric gaze labels. IJCV2023 Gaze Plus is a dataset that captures egocentric video of people preparing food in a kitchen setting. Ego4D is a larger dataset that contains egocentric video of social interactions between the camera wearer and other people. We follow previous works and produce a model output of downsampled resolution, which is then upsampled to match the input dimension with trilinear interpolation. For ground truth, we use a Gaussian distribution centered at the gaze location, and we train the model with KL divergence loss. We use pre-trained parameters from training on Kinetics 400 for initialization. We also use standard data augmentation operations. Our evaluation metrics are F1 score, recall, and precision. We explore four strategies for embedding the global context in our experiments. Strategy A uses max pooling on the input directly. Strategy B conducts max pooling on unflattened local visual tokens. Strategy C uses a sequence of convolutional layers on the input directly, and Strategy D uses a sequence of convolutional layers on the unflattened local visual tokens. In our experiments, we evaluate the F1 score results on the two datasets. The first 5 comparisons in this figure show the results of our 4 global embedding strategies as well as a baseline model with no global context. All of the 4 strategies bring gains to the baseline model that doesn't use global context on both datasets. We find that strategy D, which uses convolutional layers on local tokens, results in the most improvement. Hence, we continue using this embedding in our experiments. One might suspect that the gains we see are from the additional layers and parameters in the global local correlation module. To make a fair comparison, we implemented another baseline that adds an additional layer with regular self-attention. As we see in the last 2 comparisons in this figure, the model with the global local correlation module outperforms this baseline. This validates that the improvement comes from explicitly modeling global and local correlations rather than simply adding more parameters. We further compare our model with prior state-of-the-art approaches on IJCV2023 Gaze Plus. The proposed model exceeds the best CNN-based approaches by 3.9% on F1, 9.3% on recall, and 3.5% on precision. This shows the superiority of utilizing a transformer-based architecture in egocentric gaze estimation and incorporating global scene context into the model. We see similar results on the Ego4D dataset as well. Our model outperforms prior state-of-the-art approaches by 5.6% on F1, 4.5% on recall, and 5.5% on precision. We also qualitatively evaluate our model through visualization. In comparison with other models, you can see that our model, which is on the right, makes more precise and accurate predictions at the gaze fixation point. The other 3 approaches we compare with make incorrect predictions or overestimate the gaze area. We further study what is learned in our global local correlation module by visualizing the correlation weights of the 8 attention heads of the multi-headed attention mechanism. In this visualization, highlighted areas suggest local regions with stronger connections with the global context. The region of the gaze target itself is well captured by some heads in both examples. We find that there are also a few heads that encode visual features that lie in the background of the scene. This can help the model avoid missing important global cues. Finally, we visualize our model's predictions on the input videos to show our model in action. The green dots represent the ground truth fixation points, and the overlaid heat maps are the output of our model. In conclusion, we build the first transformer-based network to address the challenging task of egocentric gaze estimation. We utilize a global visual token embedding strategy to incorporate global scene context into our model. A novel global local correlation module is designed to explicitly model correlation between global and local features. Our model outperforms prior methods by at least 3.9% on EGTEA Gaze Plus and 5.6% on Ego4D. We provide more insights of the proposed global-local correlation module, which indicates it captures gaze features by assigning different weights to global features. Thank you for watching this video.